Hello everyone, myself Rahul K. Sarthi. I am from Sri Venkeshwara College of Engineering, Bangalore, from Electronics and Communication Department. Today I am going to discuss the seminar topic Energy Harvesting in Underwater Acoustic Wireless Sensor Network under the guidance of Professor Swapna CH, Assistant Professor, Department of ECE. These are the contents includes introduction, extensive literature review, objectives, proposed methodology, results, applications, conclusion and reference. These are about the introductions. Energy harvesting is a promising solution for powering the underwater wireless sensor networks as it allows sensors to extract the energy from the surrounding environment and it convert it into the electrical energy. Energy harvesting methods for underwater wireless sensors includes solar, thermal and mechanical energy harvesting. But the most promising method for underwater environments is acoustic energy harvesting. Acoustic energy harvesting involves capturing sound waves and converting them into electrical energy using piezoelectric transducers. Energy harvesting techniques have become increasingly important for IoT devices due to their many advantages, and the energy harvesting in underwater wireless sensor networks can also help to reduce the environmental impact of underwater sensors by eliminating the need of disposal batteries. Energy harvesting in underwater wireless sensor networks is still its early stages of development and faces many technical challenges such as low power density of ambient acoustic energy and the limited energy storage capacity of current energy harvesting system. Acoustic energy harvesting can be used to power power the low power sensors and wireless communication modules in underwater wireless sensors, allowing for continuous operation without the need of battery replacements. Acoustic energy harvesting can be used to power a variety of sensors and communication modules in underwater wireless sensors, including the temperature sensors, pressure sensors, and acoustic modems. These are the extensive literature review which I have referred. In that, firstly, underwater generator for submersible sensors by the published by the authors C.L. Flaria and M.S. Martins in the year 2021. This paper has its pros like higher power output. An underwater generator can provide a higher power output compared to batteries, which can be beneficial for powering sensors that require more energy. And this paper has its cons also. Depth limitation. An underwater generator may have depth limitations and it may not be suitable for sensors that need to operate at great depths. And the next paper is underwater ultrasonic wireless power transfer, a batteryless platform for the internet of underwater things, published by the author R. Gaida and N. Dev and T. Melodia. And this paper has its pros like long distance transfer. Ultrasonic waves can travel long distance underwater, enabling the power transfer over longer distance than other wireless power transfer technologies. And this paper has its cons also like environmental factors. The effectiveness of ultrasonic waves can be affected by the environmental factors such as water temperature and salinity. This can impact the reliability of the power transfer. And the third paper is self-sustaining acoustic sensors with programmable pattern recognition for underwater monitoring. It was published by the author P. Mayer and M. Mango and L. Benini. And this paper has pros like self-sustaining. This type of sensors is designed to be a self-sustaining, which means it can operate for extended periods of time. And it has cons like vulnerability of noise. Acoustic sensors can be vulnerable to ambient noise such as that produced by the ships or marine lives. And the next paper is a survey of underwater multi-robot system. It was written by Z. Zoho and J. Leo in the year 2022. This paper has its pros like increased robotness. Multi-robot systems can be designed to be more robot and fault tolerant than single robot system. And it has a cons like maintenance. Maintaining multiple robot can be more challenging than maintaining a single robot. And the next paper is recent trends in underwater visible light communication. It was written by M.F. Ali and D.N.K. Jayakodi and Y. Lee in the year 2022. It has a pros like low power consumption. UVLC system can operate at low power levels, and it has a cons like limited range. The range of the UVLC system is limited by the attenuation of visible light in the water. These are the objectives: to identify suitable energy sources for underwater wireless sensors and networks and develop energy harvesting techniques that can effectively extract energy from these sources, to design the optimized energy harvesting system that can operate in harsh underwater environments and are reliable, efficient and cost effective, to evaluate the performance of energy harvesting system in underwater through simulation and experimental studies and compare them with battery powered systems, to explore the integration of different energy harvesting techniques and sources to create hybrid energy harvesting system that can generate power from multiple sources. This is about the proposed methodology. Underwater nodes are generally battery powered. Energy harvesting as a vital role as it directly enhances the battery lifetime, and it can even power the sensors nodes without batteries. To harvest energy on the surface of water or within a water body, a number of techniques have been utilized. They are, for instance energy harvesting from turbine, temperature variations in water, piezoelectric materials, solar radiations, ultrasonic radiations. The signal coordinator performs a number of tasks. It defines a certain threshold for the generated power, and its calculations converts AC to DC signals in case the harvester uses digital circuitry and computation and conversion from altering to direct current. The input energy execution originates from an external source of energy. For instance, input energy excitation may arise from temperature variations, pressure on a piezoelectric material, kinetic energy of waves to drive a turbine, or chemical reactions from microorganisms present in the water, among the many. The input excitation is converted into electrical signals by a transducer. The ambient energy sources are available in the environment and can be easily accessed without any costs. And this is the black diagram, and this includes transducer, signal conditioner, and temperature management, power management, and powering electronic device. Piezoelectric based harvesting. This is the black diagram for energy harvesting based on piezoelectric. Piezoelectric based harvesting is a popular method for generating electrical energy from mechanical vibrations in underwater acoustic wireless sensors. It includes underwater acoustic sensors. The sensors converts the mechanical pressure waves into an electrical signals that can be processed by harvesting system, and it also includes the piezoelectric transducer. It is responsible for converting the mechanical energy from underwater acoustic signal into electrical energy. And it also includes a rectifier and voltage regulator. The rectifier circuit converts the AC output voltage from the piezoelectric transducer to DC voltage. The voltage regulator circuits ensures that the output voltage is stable and within a specific range. And energy storage unit. The energy storage unit is responsible for storing the harvested energy from the piezoelectric transducer. And the last and final is power management unit. The power management unit controls the flow of energy between the energy storage unit and the sensors. It ensures that the sensor is supplied with a stable and regulated voltage, and that the energy storage unit is charged efficiently. And the next is energy harvesting from ultrasonic radiations. This is the block diagram for energy harvesting from ultrasonic radiations. This includes ultrasonic transducer, receiving transducer, rectifier, and power management, and load and energy storage. The first one is transducer. A transducer is used to convert the ultrasonic waves in water into electrical energy. It can be a piezoelectric transducer or magnetostrictive transducer. Next one is rectifier. The rectifier circuit is used to convert the AC voltage generated by the transducer into the DC voltage. The DC to DC converter. The DC to DC converter is used to step up or step down the DC voltage generated by the rectifier to a level suitable for powering the load. Load. The load is a device that is powered by electrical energy generated by the transducer. It can be any electronic device such as a sensors, transmitters, or data logger. Next, energy storage. An energy storage device such as battery or supercapacitor may be used to store the electrical energy generated by the transducer. This is useful for applications where the load requires a higher power than what can be directly supplied by the transducer. These are the results. Maximum power harvesting capability of compared techniques on the logarithm scale. The logarithm scale is used for better overall presentation of harvested values. The category of AUV or kinetic energy harvest the maximum power. The kinetic energy from water is ubiquitous and therefore is conveniently utilized. The physioelectric energy which harvests energy directly from the underwater harvest the fourth maximum possible amount of power which is about 125 watt, and this is the graphical representation of energy harvesting techniques in underwater. Minimum power harvesting capability of the compared techniques on the logarithmic scale. The logarithmic scale is used for better overall presentation of harvested values. The physioelectric technique harvests the minimum power. The power values harvested by ultrasonic radiations, hybrid techniques, turbine, and marine life are 80 watt, 40 watt, 1.6 watt, and 0.190 watt correspondingly. And these are the applications. Environmental monitoring. Energy harvesting can be used to power sensors that monitors the environmental conditions such as water, temperature, pH, and salinity. And next one is improving reliability. Energy harvesting can also improve the reliability of underwater acoustic wireless sensors networks by ensuring that sensors always have access to power, even in remote condition or in a harsh environmental conditions. Next one is underwater communications. Energy harvesting can be used to power sensors that enable the communications between underwater devices or with surface-based communication systems. And the next one is underwater navigation. The energy harvesting can be used to power sensors that provide navigation information to underwater vehicles or unmanned underwater vehicles. And next one is oceanographic research. Energy harvesting can be used to power sensors that collect the data on ocean currents, tides, and other oceanographic parameters. And these are the conclusion. In conclusion, energy harvesting can provide a viable solution to energy constraints faced by underwater acoustic wireless sensor networks. Energy harvesting techniques such as solar, thermal, and mechanical can be used in underwater wireless sensor networks. Solar energy harvesting is a promising technique due to its availability and abundance in the ocean. Energy efficient communication protocols and routing algorithms can be used to reduce the energy consumption of underwater wireless sensors. The integration of energy harvesting techniques and energy efficient protocols can prolong the lifetime of underwater wireless sensors and enhance their performance. The use of multiple harvesting techniques and hybrid energy storage system can further improve the energy efficiency and reliability of underwater wireless sensors networks. Overall, energy harvesting can be a valuable approach to overcome the energy constraints in underwater wireless sensors networks and enable long-term sustainable operations. These are the references I have referred. Thank you all.